Okay, so today we are going to take some notes. Next couple days will be a little lecture heavy, just because we're getting into it to a point. We're also going to do this exercise. Kind of got to move quickly on it. Don't let it overwhelm you. Homework tonight, chapter 5. Remember from this last time, chapter 4. Make sure you make up the test we took last time. But chapter 5, read it, and your Cornellis. That is the homework for tonight. So we should have everything away except notes. Remember, this is our first set of notes for chapter 4, 5, and 6. Forces. So before we talk about Galileo, we need to talk a little bit about Aristotle. Now, Aristotle kind of gets a bad rap in a lot of science books. Read about it, and it always makes him sound like he was kind of some sort of fool. Aristotle wasn't. Aristotle was a genius. He made great observations. He had a lack of knowledge that we have today, but his observations were valid, and he made good conclusions based on those. He was a very smart man. He was the tutor of Alexander the Great. He did a lot of things too. You gotta say something for a guy who conquers most of the known world when he's in his 20s. So Aristotle made good observations. He watched things, he dropped things, and he said, well, when I drop these two things, the heavier one falls faster. In fact, if I took you to the Golden Gate Bridge and handed you a light ball and a heavy ball, which is going to hit the water first? Heavy ball. And you would come to the conclusion, well, heavier objects fall faster. And we know that's not true, but it is true if you have air. Now, Aristotle didn't understand about air. They didn't know anything about air or anything like that. Didn't come into account. He also knew that when you make something go, in order to keep it going, you have to keep pushing it. Which is true, you do, because there's friction, things like that. So the observations he was making were good, and he made good conclusions based on his knowledge. But that's one of those hallmarks of science. As we go on, we learn more things. Those ideas might be superseded. So some of these gave way, especially when we started on this guy Galileo. So Aristotle, about 3,000 years ago, that's when he lived, approximately 3,000 years ago, something like that. Galileo, about 500 years ago or so, give or take, a decade or two. So Galileo, he gave us this idea that force is not required to keep an object moving. When he said, look at this, it's like, well, if I go down the hill, things speed up. If I go up the hill, the ball slows down. What if there's no hill? Okay, go down the hill, go up the hill. What if there's no hill? This is what he was thinking about. What if there was no hill? You don't need more time? He showed that an object rolled down the ramp will come back to its same height regardless of how far away it is. But again, we have that caveat. In the absence of friction. And if you use like a steel ball on a steel plate, is there very much friction? No. It's like the bowling ball. If I had an infinitely long bowling alley, bowling ball has very little friction. It's going to roll a very, very long time. In fact, the only thing that stops the bowling ball is when it hits the wall behind. Not even the pins slow it down appreciably on that. It's why the most efficient form of land transportation. Anybody know what the most efficient way to ship things on land is? By what? By train. Train is the most efficient land form. Steel wheels on steel rails is the most efficient form of land transportation. Most efficient transportation is a ship, but it's hard to take a ship across Kansas, or Minnesota or someplace like that. You might want to put diagrams or just note where they are. This is figure 4.3. It's why it's always good to have the book open in these chapters when we're going through them. But the idea here is that when he said, okay, if I roll the ball from here, it's going to go up to the same level. Even if I increase the length of the ramp by moving this angle out, it will still move until I get to the top here. But it's like, okay, what happens if I never had that second ramp? It would keep going forever. This is this whole idea that, and once it gets to the bottom of the ramp, is there anything pushing it? No, there was nothing pushing it. Once it got to the bottom of the ramp, it just keeps going forever. It doesn't need any force to keep going. This is where Aristotle didn't understand friction. In the absence of friction, it's going to keep going. It's going to keep going. Anyone need more time on this side? So, Galileo showed that this property of an object to resist change in motion, in other words, you need something to make it change motion, he called inertia. Inertia. And inertia kind of means lazy. And that's what the word really means, is lazy. Lazy. Does not matter, does not like to change its state of motion. Now, inertia is a property of mass. If you have mass, you have inertia. In fact, we measure inertia as mass. You know, how much inertia does something have is mass. Mass is the amount of matter. How many molecules, how many atoms, how it's in there on that, is in that substance. And we use as a symbol the letter M. Letter M. Mostly we use the lowercase m, but you will also see an uppercase. M, the letter M, whether it's upper or lower, it's usually, it's the only thing we use M for, is for mass. You'll see uppercase M when we get like the universal gravitation, when we're dealing with two different masses. Usually we use a capital M for what we call as a field mass. In other words, it's the mass that's creating the gravitational field that we're trying to measure. Our unit is the kilogram. We measure mass in kilograms. All our masses are in kilograms. Anyone need a little bit more time? A very long introduction on this one that talks about all the segments.
Physics is about movement, how things move and why things move. Here is a very large thing. What do you notice about it? It's not moving. Go ahead and try and move it. You can't. It doesn't want to move. Is that because it's so large? Try and move a smaller thing then. Well, you managed to move that a little way, but it was a great effort. It was as if it still didn't want to move. Even tiny things are reluctant to move. Even a pebble takes some effort to shift. This is the first rule of physics. Things like to stay where they are. Unless there is some force to push or pull it, no object in the universe will start moving of its own accord. It's as if all objects were lazy. But why is physics about movement if nothing wants to move? The answer is that there are lots of things in the universe that pull or push on objects and force them to move, whether they want to or not. You force the pebble to move. And since things are lazy, you'd expect your pebble to try and stop moving as soon as possible, wouldn't you? Well, you'd be wrong. Strangely enough, although when the pebble was at rest, it wanted to stay at rest. Now that it's moving, it wants to keep on moving. In fact, it would like to keep on moving forever and ever. The only reason it slows down and eventually stops is because things in its path force it to stop. The resistance of the air, or a tree it bumps into, the roughness of the ground. But if there were no air or rough ground or trees to get in its way, if you were in outer space, for example, when you kicked your pebble, it really would go on moving forever and ever. It would never stop. So how can we say that objects are lazy? If the pebble's moving, it's not being lazy, is it? Yes, it is. It takes just as much effort to stop moving as to start moving. You get a feeling for this when you're ice skating. When there's hardly any resistance to your movement and it's easier to keep on gliding along than to stop. The same goes for the pebble. If nothing gets in its way, if nothing helps it to stop, it will have to make all the effort to stop by itself. And it's much too lazy to do that. We can now modify the first rule of physics from things like to stay where they are to things have to keep on doing what they're already doing. If a thing is at rest, it wants to stay at rest. If it is moving, it wants to keep on moving. In other words, there is lots and lots of laziness in the universe. Physicists have a special word for laziness. It comes from Latin. Inertia.
Okay, so write your summary, just a couple of lines as a summary for... When we measure mass, we use a balance. Our balances don't look like this, but this is what a balance really is. Those electronic balances are a little different. Now this balance is actually in the Wells Fargo Museum in Sacramento. And this was used for like when gold miners would bring in their gold, and this is what it's made to do. So they would put the gold on one side, and you see these all these little masses, and they would pile the little masses on that side, and when the whole thing balanced, they knew that this gold had that mass on it. Think about this. If I brought it to the moon, would it work? This would work fine. In other words, if I have 1 kilogram of mass, it would work fine on the moon. It would work fine on Jupiter. Would it work on the space shuttle? No. It still need gravity pulling down. But we're not measuring that. Our little balances, actually, our little electron balances, if I brought it to the moon, would it mass properly? No, because our little balances are actually what's called a scale. Scale is what you measure weight on, and they're just calibrated to grams. An electronic scale, an electronic balance, even though we measure mass, is really a scale. Balances are balances, and literally it's what it is. It has to balance like a teeter totter. But what is mass not? This is where people get confused. Mass is not volume. Mass is not volume. Volume is the space something occupies. Matter, remember, mass is matter. How much stuff, how many atoms are there. So if I took a lead box and a pillow, and I compared their masses, so and I'm going to take 1 kilogram of each. I have 1 kilogram of each. So I have the mass, I have the volume of each. Well, what can I say about the volume of the lead compared to the volume of the pillow? Is it going to be greater, less, or equal to the volume? Which one's going to have a greater volume, the pillow or the lead? Volume. Lead, pillow. Which takes up more space? The pillow. The pillow has a much greater volume. Much greater volume on that. I mean, just think the mass we use. Our little hex masses are like a kilogram. They're about this big. If I took a kilogram pillow, pretty big. But what about their masses? What could I say about those? They are the same. They have the same amount of matter, different volumes. Okay, this is different. Mass is not volume. Volume is that space. Mass is not weight. Weight is the force of gravity. They are not the same thing. Mass is how much matter. Weight is the force of gravity. Mass does not change with location. If I was using that balance, I showed you the previous slide, if I had 1 kilogram on the Earth and I brought it to the moon, it would still be 1 kilogram. I'd still have to put the same amount of masses on the one side as I had on the other. If I brought it to Jupiter, same amount. If I brought it to Mars, same amount. And even though the balance doesn't work very well in the International Space Station, if I went to the International Space Station, if I have a mass of 1 kilogram, do I still have a mass of 1 kilogram there? Yeah.
Yes.
That's how many atoms. The only way I can lose mass is if I start hacking things off of it. Mass doesn't change No matter where you are, your mass is going to be the same. Weight changes with location. I mean, even on the Earth, do you weigh the same everywhere on the Earth? Remember what we said, the value of g, acceleration of gravity. Remember what we really said about it. 9.81 meters per second squared is the average value at sea level. Average value, which means some places it's lower, some places it's higher. Not a lot, but as you go. So as you go over the mountains, it goes down. You know, things like that travel around the Earth, it goes down. You go to Mars, it's less, you would weigh less. Same mass, but you're going to weigh less. You go to the moon, you're going to weigh less. You go to the International Space Station, your weight is 0. So if you had if your mass on the Earth, that 1 kilogram mass on Earth weighs about 10 newtons. Take the moon, it weighs about 1.6 newtons. Go to Mars, it weighs about 4 newtons. On Jupiter, that 10 newtons on Earth is 30 newtons on Jupiter. 3 times the gravity on Jupiter. Space station 0 on that. So, on all those things. Yes, sir. Kind of. Well, you have other things to worry about Jupiter. It's like, what constitutes service to Jupiter? Then you have other issues to worry about. But yeah, if you were under 3 times the gravity, now you may not get squished, but you're going to be hating life. You know, it's like when you take off on an airplane, you know how you feel like heavier, stuff like that. Because if you were on a scale, you would weigh more at that instant, but it goes away after time. So it's like airplane pilots. They say, well, this guy's pulling 5 Gs. That means he's pulling 5 times the acceleration of gravity. It means he feels like he weighs 5 times more than he really does. So if you weighed 100, you know, if you're 100 pounds on the Earth under 5 Gs, it feels like you weigh 500 pounds. So it's much harder to move, and it's like where it might be easy to pick this up on Earth, it's only going to be 3 times harder to pick it up on Moon. Conversely, when you go, or on Jupiter, conversely, when you go to a place like on the Moon, you ever watch the astronauts? They're all bouncing around. It's really light. I mean, even though those suits are very heavy, I mean, those suits are hundreds of pounds that they're wearing, they're still able to bounce around because everything's much lighter on the Moon. Their muscles are used to the Earth, you know. So, worry about on those kind of things. Question. Good question, though. Any other questions about that? We have another little video about mass.
Eureka! The story so far. Things like to keep on doing what they're already doing. They don't like to start moving or stop moving. They are lazy. Another word for laziness is inertia. And now, mass. A large thing is equally difficult to move and to stop moving. Whereas a small thing is easier to move and easier to stop moving. The big rock has more inertia than the little rock. It is lazier than the little rock. Are all big things lazier than little things? Does inertia always increase with size? Oh, really? Well, why don't you take a huge cube of styrofoam and try to throw it? And catch it. Then do the same with a small cube of lead. You still think big things are lazier than little things? The small cube of lead was more difficult to stop moving than the big cube of styrofoam. In this case, the small thing was lazier. It had more inertia than the big thing. So inertia doesn't always equal size, or volume, or bigness. In fact, when we talk about how much inertia a thing has, it isn't really a question of how big it is, but of how massive it is. A massive rock, for instance, is a rock that contains masses and masses of stuff or matter. It's not merely big, but also solid and chunky, like a massive bulldozer or a massive ball player. You don't push things like that around very easily, any more than you can stop them easily when they come charging at you. They are too massive. Because of this, scientists took the word mass as a measure of inertia. The more the mass, the more the inertia. In spite of the fact that the styrofoam cube looks much bigger and more important than the little lead cube, it doesn't contain as much stuff. There's much less to it than there is to the lead cube. It has a far smaller mass. But just how much is a lot and a little when you're talking about mass? To find that out, we have to go to a place called Sèvres, near Paris in France, where a particular piece of platinum has been very carefully preserved. Scientists all over the world have agreed to call this little chunk of metal 1 kilogram, which is very convenient, because if you take a balance and put this piece of platinum on one pan, and put any object you like on the other, a pebble, let's say, then if they balance exactly, you know that the pebble has a mass of exactly 1 kilogram. But what about the cube of lead? That feels as if it has a lot more mass than the 1 kilogram pebble. Well, all we do is put the cube in one pan of the balance, have a whole lot of copies of the platinum kilogram made up, pile these standard kilograms in the other pan until they balance the lead cube, and then count how many there are. 1, 2, 3, 4, 5, 6, 7, 18, 19, 20. There! Now we know that the lead cube has a mass of exactly 20 kilograms. Of course, we can do the same with the big important looking cube of styrofoam. 1, 2, sorry, you have only 2 kilograms of mass. So the lead cube has 10 times more mass than the styrofoam cube. Which explains why it's 10 times more difficult to push around.
All right, so write your summary to that, please. Okay, which leads us to our first physics law. Newton's first law of motion. And this one of the three actually is given another name. We call it the law of inertia, which I like to call the seatbelt law. Why we wear seatbelts. Now, Newton's first law says that every object at rest or in a state of motion in a straight line at a constant speed. Now, we call motion in a straight line at a constant speed, we call that constant velocity. So any object at rest or in a state of motion at a constant velocity will continue in that state of motion, either rest or moving, unless an outside force acts upon it. So in order to make something change what it's doing, you have to put a force on it. It will always continue doing something until something else stops it. Examples we're going to talk about both come from your car. Okay, so seatbelts. Good or bad idea? Good. Very good. And those kind of seatbelts were in cars. Cause problems. Well, why a seatbelt? Well, you know what? Let's take the example of your friend. Friend didn't have physics, so it's unwise because you are all wise physics students. You are understanding it. You understand the law. Now, there is a law in the state of California that says you have to wear a seatbelt. We're not talking about that law. I mean, you can break that law and might get away with it. It's not a good idea. We're talking about this law. This law you can't get away from. It's always going to happen. Well, let's say your friend driving they're driving the little Honda Civic up Woodside Road, and going around the corner, he's driving the speed limit. So he's not totally unwise, but not wearing a seatbelt. Driving the speed limit. And you know, one of those little antlered rats that like to jump out in front of you, let's call it Bambi, and jumps out in front of you and hits you. You hit it. Bambi puts a force on the car comes to a stop. Well, inertia says if my motion can be stopped, puts a force on it. Now the car stops. But your friend, now remember, your friend, the car, and everything else had basically 30 miles per hour worth of inertia. Bambi stopped the car. Did Bambi put a force on your friend? No, your friend's going to keep going forward with 30 miles per hour of inertia. Because even though the car stopped, your body started to stop. His body said, hey, law's on my side. Law says I have to stop. I have inertia. I'm lazy. Keeps going. He's going to keep going until something puts a force on him. You know, steering wheel, windshield, Bambi's antlers. You know, so these things happen. You guys know that deer are the most dangerous wild animal in North America, right? More people are killed by deer than any other animal. Hitting with cars. Yeah, deer kill more people than anybody else, any other animal in North America. But now you guys, instead of that, you're driving your Honda Civic. You're driving up Woodside Road, but because you are wise physics students, you understand the law. You're wearing your seatbelt. Now, say anything happens to you, because this happens a lot. I mean, let's face it, a lot of people hit deer up there. But car comes to stop, just like your friend. Do you keep moving forward? Yeah, you do, because nothing's put a force on you yet. But you are wearing your seatbelt, so you start moving forward, you run into the seatbelt. Seatbelt puts a force on you and brings you to a stop on that. Now remember, the airbag's going to do nothing. If you don't have your seatbelt, airbag comes out, you hit the airbag, you're still going to hit the steering wheel. Airbag is only designed to keep you from making a face plant into the steering wheel. That's really its goal in life, is to keep you from basically hitting your face into the steering wheel or into the dashboard and things like that. It's not meant to stop you without the seatbelts. Seatbelts are still the primary thing here. So that's why we wear our seatbelts. Now, a headrest. Now, you turn 16, and you're thinking, hey, you go to Dad and say, Dad, 16, got my license, I get good grades, so I don't cause any trouble. I really think I deserve a car. Now, you have your eyes on Dad's 2008 Beamer, thinking Dad's going to give me the Beamer, he's going to buy himself a new car and all that. Dad takes you to service locker, he opens up the door, and there's 1972 Honda Civic. 2 or 3 ton car. He brings out, guess what? This is the car his parents gave him. He's been saving it for you. Then you have a headrest on the seat. It's old. Now you're wearing your seatbelt. It's good, but you're out here on Woodside. You're about to try to make this turn off Churchill onto Woodside Road, and you're stopped the light, and you're just kind of chilling there, waiting for light. Well, someone else is coming out. They're texting while they're driving. Texting while you're driving, they say impairs you more than being under the influence. Texting while driving impairs you more than drinking and taking drugs. I would say you should be doing those either, but it impairs you more. So this person's texting, right? Hey, let's go to Starbucks. Car's driving back to your car. Let's hope they have their seatbelt on. But they hit you. Now they put it. Your car was stationary. Everything in your car was stationary. Hits your car, pushes you forward. Now, does your body want to move? No. But your body has seat against it. The seat pushes your body. But you have this big melon up here. It's very massive. And it's attached by this little piece of spaghetti. Now, your body starts moving forward. And your head goes, I ain't moving. I'm at rest. Law says I don't have to move. I'm not going to move. So your legs stay still, your body's moving forward. Well, can you see the problem here is your body's moving forward, and this is stretching. So eventually it's like, I'm going to get pushed forward. So you get whiplash. Could break your neck. It happened to my dad when he was, when he was like in his early 20s, car wreck. They didn't have headrests on cars those days. Got hit from behind. He actually cracked his neck. But you can see, so in whiplash, you can see all these things. It's like you think, well, my head went back. No, is your head going back? No, your head's not going back. Your head stays still. It's your body moving forward because whiplash. By the way, this is the same reason. You ever go? They have that roller coaster at Disneyland, the California Adventure. It like shoots you out really quick. What do they tell you to do just before it launches? Put your head where? Back against the headrest, because if you go, bam! You get hit the headrest. That's why, because when the thing moves forward, your head doesn't, and the car is going to whack you. But this is also why we have a headrest. So cars now, they have a headrest. They even put a headrest in the back seat now, because the headrest sits like right here. So even though you get hit from behind, yes, it's going to come hit you, right? Your body's moving forward. Your head isn't moving anywhere. It's not your head that hits the headrest. It's actually the headrest that hits your head. But when it hits your head, after a little bit, is it going to start pushing your head forward? Yeah, and your head's just going to stay with the rest of your body. And you're going to move forward. But that's what the purpose of the headrest. Because of the first law. Because of the first law on that. Okay, the headrest is not just so you can lean back and look cool. It's so you don't get whiplash and things like that. All right, any questions about the first law? Which leads us, what causes that motion? To make something move, we must apply a force. A force is based most simple form. It's a push or pull. Force is what causes motion. And our symbol for force. Now I use F for all forces, and I might add a subscript for what flavor of force we're talking about. Force of gravity, use a G. Force of tension, use a P. Force of friction, use an F. I don't like to use other symbols other than F because it kind of confuses things. At least if you're always using an F, it's a force. Your book will sometimes use other symbols, which can be other things, other places. It gets confusing. Our unit is the Newton. We honor Sir Isaac Newton for naming this. And this is our first unit named after somebody. Notice our symbol is a capital letter. Whenever we name a unit after somebody, we use a capital letter. Notice meter was always small. Seconds is small. The kilogram is small. Capital. Now the thing here is, when you say Newton, Newton does have what we call those SI dimensions. Remember we mentioned that in chapter 1. Things have SI dimensions. So when you say 1 Newton, what you're really saying is 1 kilogram meter per second squared. So a Newton is a kilogram meter per second squared. But instead of having to say a kilogram meter per second squared, kilogram meter per second squared, we just say Newton. But this is also why when we do our calculations, why? Mass has to be in kilograms. Distances have to be in meters. Time has to be in seconds. Because if our mass, distance, and time are not in those units, it's not a Newton. To be a Newton, it has to be a kilogram meter per second squared. All right, this is our MKS system. Now, force is a vector. Kind of makes sense. Does it matter what direction I push something? Well, let's see. If I try to push my cart towards the yellow flag over there, and I'm pushing this way, am I going to get there? No. So if I'm pushing that way, and I really want to go that direction, and I'm not getting there. Well, yeah, I guess I could go the long way. But then I actually end up on the other side of the wall. Take a while. Now, net force, which is one of the things we're going to be calculating today in today's exercise, is what we really deal with. You have a net force on you right now. You have a net force of 0 right now, because you have actually something pushing you down, pulling you down. You have something pushing you up on that. So net force is the sum of the forces on an object. We might have a number of forces acting on us. And it's those sums tell us where we are going and what we are doing on that. Anyone need more time on this slide? Anyone need more time? So let's show a couple of examples. So I have this box here. I put 10 newtons that way, 5 newtons that way. Now, notice they're going in opposite directions. So remember we're dealing with velocity vectors. If one direction was positive, the other direction had to be Negative. Same thing with force. Generally say anything to the right is positive, so anything to the left is going to be negative. Does it matter which we make negative, which positive? No, just as long as they're opposites. We usually make right positive because if you think of Cartesian coordinates, the x-axis, right is positive, left is negative. That's just where that comes from. So our F net here is going to be that negative 5 newtons plus 10 newtons, or a positive 5 newtons, which means my net is that 5 newtons to the right. I know it's to the right because it was positive, and I've said positive is right. All right, so I have this, and again, to the left is going to be negative. So my net force. And notice how I use the little subscript. F net. So I get that negative 20 newtons plus 5 newtons plus 10 newtons is going to equal negative 5 newtons. So I get negative 5. So my net force would be 5 newtons to the left. It's left because it came out negative. And this is how we do this. This is where also all that vector stuff and the triangles and the things like that come in. Any questions so far? Anyone need more time? But what about this case? Our net force there is 0. I have a question. You're moving or not moving?
Moving.
Can you tell from the information I've given you?
No.
No. Well, if your answer is right, it could be moving, not moving. Again, net force does not tell us anything about its state of motion. It may not necessarily tell us about state of motion. Okay, there's other factors on that. Which leads us to this idea of what's called equilibrium. Net force of 0. When net force is 0, we call that equilibrium. Equal. All the forces equal out. Now the thing is always to remember, equilibrium, V is constant. V is a constant. It's always a constant velocity. Because like this, right here, the tape. What is the velocity of that tape on my desk? 0. Is that constant velocity? Yeah, it is. 0 is a constant velocity. Constantly going 0. Things on my desk are at static equilibrium, just as you are at static equilibrium in your chairs. In your chairs, you have a force pulling down, and you have a force pushing up. And they are at static equilibrium because you're neither going up and you're not going down. You're static equilibrium. The things on my table are static equilibrium. In this case, V would be 0. Acceleration is 0. Remember, we said to be stationary in the last chapter. When both are 0, we're stationary. Dynamic equilibrium, we're moving. V is not equal to 0, so it's any value other than 0. But remember, acceleration is still 0. Net force, acceleration is 0. We're moving at a constant velocity. Now we're still moving, but it's constant velocity on that, which means all the forces are equal. In fact, we're going to do a lab about friction, and we're going to use this fact that if I pull force one way and friction can pull back the other, if we're pulling at constant velocity, I know whatever I'm pulling in must equal the friction on that. All right, questions? So right now, if all the groups, if one person from each group can come get the little green box and a meter stick. Come get the green box and a meter stick. Do not put your notes away. Background, we're going to put our tables and get started. So, we are dealing with basically how strong is a spring. Hooke's law. Hooke was a contemporary student. And do not pull on the scales and stuff like that. Pulling on the scales can damage the springs inside. You really don't want to have to pay for a new one. But don't pull on the scales, just like you don't yank on the springs and stuff like that. We leave because you can damage the springs inside these. So Hooke's law. Now Hooke was a contemporary of Newton, sometimes a rival of Newton. They lived about the same time. They're both English. And what Hooke discovered about springs, and we applied also to elastic, how strong a spring is that he said, well, the force you place on a spring is directly proportional to how much it moves, its displacement. They're directly proportional. The more force, the more it stretches. Conversely, we apply this to all elastic materials, even rubber bands. You know, how much a rubber band stretches uses the same principle. We're dealing with the type of spring that we pull apart, like this. Now, there are types of springs also compression springs. They get pushed together, twist them. And it's very important that you have the right strength spring for whatever application, because if you have a garage door and you have put too strong a spring on it, what happens? When you lift it, all of a sudden, whoosh, it gets away from you. If you have one that's not strong enough, and also it would be very hard to pull down again. If you had one that was too weak, it would be very hard to put up, and it might fall down on you. Things like that. So there's different kinds of springs, different kinds of applications. Like if you go to Orchard Supply, you might see this whole section of springs, and they all kind of look alike. What's the difference? Well, different springs have different strengths. It's like even you're going to use this long spring, but it has a different strength than the spring that's inside your scale. By the way, scale, measuring force, that's what it does. So to make them equal, though, we use what's called a proportionality constant. And we use a lot of proportionality constants. This one, it depends on the spring. We give it the letter K, and we call it the spring constant. Now, one of the things you're going to be doing is calculate. You're going to find the spring constant two ways. One way is with the equation. Right? You're going to have a force. You're going to have the displacement. You're going to calculate out the K and then find the average. Another way is to graph it. You're going to graph the force versus the displacement, and the slope of that line is going to be that. So right now, we're going to take about 3 minutes. You need to put all this graph stuff into your note. Basically what we're doing here is we're just going to find the strength of the spring. That's what we're doing here today. There's no problem, no hypothesis. We're just practicing. This is what a material scientist would do if they made a new spring. But there shouldn't be anything out of the kits right now. We should be putting this into your notes. This goes into your lecture notes. This is an exercise. So let's take about 2 or 3 minutes and get this all into your notes, please. So this side is we are measuring our measurements. And you're going to number these, and you really want 10 down. You probably only put 3. But it's 3, 6, and you're going to go down to 30. So you need 10 little blocks, which is okay. You're going to just draw more. Sorry about that. But you should go down to 30, so 10. You're going to need 10 little blocks. They don't have to be, I don't care if there's other things there. It doesn't need to be pretty. It just needs to be. No. All right, so 10 down on that. These have like the last 2 answers. So you're going to find the distance. Now, first of all, we're find where is it on the meter stick when it starts. And then we're going to measure how far does it go down every time I add some weight. How much does that weigh? Then we need to find the displacement. In other words, how much did it move? Which means this value minus the force. Wherever it started from, because we want to know how much moved. That's the displacement. This is our delta x, which is also the x on our graph. The force. Well, we want to know basically, we don't know what to include the weight of the spring and everything. So we have to subtract this part, which is the spring. We just want to know what the weight of the washers is, which is this one. This is F, which is our y column. So these two values go up here to find K for this last column. Just do a little algebra. I give you force, you got delta X, find K. The other one, you're going to be plotting these, and you're going to choose linear. For the graph, you're just going to choose linear and record the slope of the line. Make sure everybody in the group gets a copy for their notes on that. But how do you set it up? So we're all going to set up together. You make sure you use this side of your meter stick, the metric side. 0 is on top. Take the force scale. There's a big hook, little hook. So one of the people in the group just holds it even at the top. That's their only job, is to keep it even so you can record it. Next comes the spring. Spring. You guys can put off the spring. This one's still a little different. You're going to hang. You have a piece of string. And then you have a little piece of wire that looks like a T. And you just hang it on the end. Like this. Alright. So you hold this, you look, okay, where is the bottom of the spring right now? That would be your starting distance, whatever that is. And we want to measure in meters, so like this, mine's at 52 centimeters, so I would record 0.52 meters. Up here, I would look at the scale, and I notice, oh, that's half a newton. So I record 0.5 newtons. That would be my start here. So 0.52 meters, 0.5 newtons. And so this is the value I'm going to subtract to get those values. So my distance minus that will give me displacement. My force minus that will give me the net force. All right, so you're always, each time you're going to subtract that one. Then, once I get that value, I can just take off, try not to drop it, this is why it takes a couple of people. You take off the little spring, this little guy here, on that, and you just have to run, and you run the washers just through here. You put 3 on. 1, 2, 3. 3 on there. And then you're going to do the same thing each time. So we have our 3, we have our scale, and we put it even. So now we look, okay, so my first trial, so with 3, I'm up to 1. Now I have 1 newton, and I look down here, and it is stretched to 53 centimeters. So now this was 1 newton, 0.53, which means when I go over here, 0.53 minus 0.52, 0.01 was my delta X. 1 minus 0.5. My net force is 0.05, and so on. Going to fill up those columns, 10 pieces of data. Once you gather all your data, and you might want to have someone in your group crunching the numbers for you. Once you gather that, put your kit back on the thing, go grab your computer, find that one, find the one by graphing, and then write a conclusion. Once you get those 2 answers, write a conclusion about what you did. Remember, you're doing this is what a material scientist would do if they made a new spring. They'd have to find out what its value for K was. All right? Questions? Don't forget to write your daily summary at the very end of what everything we did today. Need help? Come on, call me up, and I will give you all the help that I can. All right? So let's get to work.